11th Science Chapter 3 Classification of Elements and Periodicity in Properties Part 6 Trends in Physical Properties Part 1
Hello students, I am Madhusina, your chemistry teacher. Do like and subscribe my YouTube channel for further notification. In this video, we will be discussing about the trends in physical properties across period as well as in a group. We will be today discussing about two very important physical properties. Valence electrons along with valency and atomic radius. Students, first of all, how do we define valence electrons? The number of electrons present in the outermost shell is known as valence electron. Valency is defined as the combining capacity of the element. In other words, we can say the number of electrons lost or gained by the element in order to attain stability is known as its valency. So, first of all, let us study about variation of valence electrons and valency across a period. So first of all, let us see across a period. For this, let us take the example of second period. So in the second period, we have elements like lithium, beryllium, boron, carbon, nitrogen, I am putting down oxygen, fluorine and neon. So these are the elements of second period. If we put down the electronic configuration of each of them, lithium is 1s2, 2s1, 1s2, 2s2, 1s2, 2s2, 2p1. For carbon, we are having 1s2, 2s2, 2p2. For nitrogen, 1s2, 2s2, 2p3. Oxygen is 1s2, 2s2, 2p4. Fluorine 1s2, 2s2, 2p5 and neon is 1s2, 2s2, 2p6. Now, let us find out the valence electrons in each of them. For valence electron, we have to consider the outermost shell. So, principal quantum number n is equal to 2 is the valence shell. So, let us find out how many valence electrons are there. Lithium has 1, beryllium has 2, boron has 3, carbon has 4, nitrogen has 5. Oxygen, this is valence electrons. Oxygen has 6, fluorine has 7 and neon has 8 valence electrons. Now, let us check its valency. So, valency is basically the combining capacity of the element. We are writing valency out here. You can write the period in one line, but because the space is less, so that's why I am putting it down. Lithium can become stable. Now, every element wants to complete its octet in order to attain stability. Lithium has 1 valence electron. For attaining stability, it can either lose 1 electron or gain 7 electrons. For lithium, gaining 7 electron is difficult. So, it prefers losing 1 electron. So, valency is 1. Now, we don't put plus and minus symbol while putting valency, right? That is for loss or gain. Beryllium can become stable by gaining 2 electrons or losing 2 electrons. Losing 2 is easy. So, valency is 2. Then, for boron, either gain 5 electron or lose 3 electrons. So, valency is 3 because it prefers losing 3 electron. Carbon, Carbon can become stable by losing 4 electrons or by gaining 4 electrons, but both the process are thermodynamically not feasible, right? Because in both the cases, carbon requires more energy and has to face instability also. So carbon prefers to mutually share 4 electrons. So valency of carbon is 4. Nitrogen can become stable by gaining 3 or by losing 5 electrons. Gaining 3 is more easy for nitrogen as it requires less energy. In the same manner for oxygen, gaining 2 electron is easy for oxygen compared to losing 6. So valency is 2. For fluorine, valency is 1 because fluorine prefers gaining rather than losing 7 electrons. Neon not interested. It is already having a complete stable octet. So it will not prefer to lose or gain electrons. So valency is 0. Now, what is the periodic trend of valence electron and valency across a period? For valence electron, we can say as we move from left to right in a period, the valence electron increases from 1 to 8. And valency across a period first increases from 1 to 4 and then decreases to 0. So this is the periodic trend across a period for valence electrons and valency. Now let us see the variation of valence electrons and valency across a group. So for that purpose, let us take the example of group 1A, that is alkali metals, lithium, sodium, potassium, rubidium, cesium and francium. I can put down the shortcut electronic configuration: helium 2s1, neon 3s1, argon 4s1, krypton 5s1, xenon 6s1 and radon 7s1. So for group number 1, if I find out the number of valence electrons and valency, what do I notice? You can see every time the electron is added into a new shell, but the number of valence electron in each shell remains constant. So the number of valence electron for each element is 1. Now here they can become stable by gaining 7 or losing 1. So losing 1 is easy. So the valency of all these elements is 1. So what can we say about the variation across a group? Across a group, the valence electron remains same. Across a group, valency also remains same. Now this is for group number 1. If we are talking about group number 15 say, then in that case the number of valence electrons will be 5 and valency is 3 for all the elements. So don't get confused that valence electrons and valency is supposed to be same. No, but all the elements will have same number of valence electrons when we move from top to bottom in a group, and all the elements have same valency. That is why we say that the elements which are present in a group show similar chemical properties. Reason? Because the number of valence electrons are same. Let us study the next physical property, that is atomic size or atomic radius. First of all, what do we mean by atomic size? The distance between the center of the nucleus and the outermost valence shell is known as atomic size or atomic radius. Let us see how atomic radius varies across a period and a group. First of all, we will study the variation of atomic size across a period. Let us consider second period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. And we are putting their electronic configuration. Now, you will notice from the electronic configuration that the number of electrons are increasing with the increase in atomic number. But every time the electrons are being added into the same shell, you can notice here we are having principal quantum number 2 as our shell. N is equal to 2 and you can see, right, the valence shell here is L according to Bohr's model, right. K is N is equal to 1. But here every time the electron is getting occupied in N is equal to 2. That means L shell. So as the atomic number is increasing across a period, every time the electron is added into the same shell, number of valence electron is increasing, but the distance between the nucleus and the outermost shell is constant. As a result, the nucleus is able to attract strongly the outer electrons, resulting into contraction in size of the atom. So we can say, as we move from left to right in a period, atomic size decreases. Now let us see the variation of atomic size across a group. For this, I will consider group number 1A. Lithium, lithium, sodium, potassium, rubidium, cesium and francium. I'll put down their electronic configurations. Helium, 2s1, neon, 3s1, argon, 4s1, krypton, 5s1, xenon, 6s1 and radon, 7s1. What do you notice? The number of valence electron is same in all the cases, 1 electron. But just see the principal quantum number. That means as we are moving from top to bottom in a group, every time the electron is added into a new shell, here in the second shell, then third, then fourth, then fifth, then sixth, then seventh. So every time the electron is added into a new shell, the distance between the nucleus and the outermost shell goes on increasing. The nucleus hence is not able to attract the outer electrons. So as a result, we can say, as we move from top to bottom, atomic size increases.